Dear students, I am Meenakshi, Assistant Professor of Physics from Chikballapur First Grade College. In this session, we will discuss motion topic. In motion topic, next we will go to the acceleration of the body, how it varies in the fluid system. So here the problem is calculation of velocity of movement of an object inside the fluid when it is moving with some low speed. Here consider a small sphere of mass m when it releases inside the fluid, that is as shown in the diagram. Here two forces are acting on the object. Two forces are acting on the object. So one is resistive force that is exerted by the liquid. It is given by Fd equal to minus kV. And another force is force of gravity that is equal to mg. It is acting along downward direction. Now apply Newton's second law of motion. Since here the body is moving along vertical direction, the net force, that is effective force acting on the object along y direction, can be written as mg minus kv. Since the direction is taken positive along downward direction, therefore we can write mg minus kv. So according to Newton's second law, it is equal to m into a, or it can also be written as m dv by dt. Call this as equation 1. Here a represents acceleration of the object, that is along downward direction. Here a acceleration can be written as, that is dv by dt. After simplification it can be written as g minus k by v. Call this as equation 2. So this is in terms of differentiation factor, therefore it is called as differential equation. Now let us apply some limit of conditions, that is at the starting instance, that is at the instant when the sphere, that is when the object is just released, that is at time t is equal to 0, its velocity is also 0, that is at the starting moment. Apply this condition in equation 2. Therefore a can be written as a equal to g minus k. Since v equal to 0, substitute there. Therefore a equal to g. Call this as equation 3. Now as the time proceeds inside the fluid, when the body moves inside the fluid, as the time increases, resistive force at the instant also increases. As the resistive force increases, acceleration of the object also decreases. Therefore, here when both the forces get balanced, that is Fd equal to mg, acceleration becomes 0. So at this moment the body moves with constant maximum velocity, that is called as terminal velocity. Now we can write the expression for terminal velocity like this. So I will explain once again. When acceleration becomes 0 means at that moment both the forces get balanced. So at that instant the body attains maximum constant velocity, that is called as terminal velocity. So terminal velocity can be written as Vt equal to mg by k. Call that result as equation 4. Now consider equation 1 once again. So that is given by m dv by dt equal to mg minus kv. Now divide this equation by kv. M dv divided by k v dv by dt, that is m by kv into dv by dt equal to mg by kv minus 1. Now apply equation 4 here. So write mg by k. Here in last slide we have written Vt, expression for Vt, that is mg by k. Okay. Now substitute here mg by k. Instead of mg by k, substitute Vt. Apply equation 4 in this above equation. So after substitution, this is m m by kv dv by dt is equal to vt minus v minus 1. So after simplification, this can be written as dv versus, that is variable separables. Just transfer the similar variable on one side, that is dv by vt minus v equal to k by m dt. Call this as equation 5. Now after integration, you will get log of vt minus v minus log vt equal to minus k by mt. Now remove log on both sides, that is on left hand side log term is there, remove that one. So in order to remove log term on left hand side, take the exponential factor for the right hand side term, that is vt minus v divided by vt equal to e power minus k by m t. So if we solve this equation, you will get the expression for v, that is v equal to vt into 1 minus e power minus k by m t. Now suppose if we take the time factor as m by k ratio, then you will get the velocity of the object inside the fluid is given by v equal to 0.632 vt, that is 63% of vt when time factor is t equal to m by k. Now similarly, if you do the calculations for acceleration of the object, you will get a equal to g e power minus kt by m. So in this equation 8, if you observe clearly, a acceleration of the object, it depends on the time factor, that is exponentially. That is exponential term always indicates the slow variation. Slow variation. So if we substitute at t equal to 0, a equal to g, that is at the starting moment. If we increase the value of t, suppose if t becomes infinity, then a equal to 0. So these are the expressions for velocity and acceleration of the object when the body is moving at slow speed inside the fluid. Okay.